Hi, in this video we are going to see a concrete example and illustration of the Edmonds-Karp maximum flow algorithm. So basically we have this original graph GVE with the V vertices and E edges, and basically at the beginning we initialize every flow to be 0. So we have the source, we have A and B vertices, and we have the T sink. And it's very important that at the beginning the residual G prime graph is basically the same as the original G flow network. Okay, so basically what's the algorithm? We have to find the augmenting path in G prime, so in the residual network. Then we have to add the given flow in G. Then we have to reconstruct the residual network G prime accordingly. And basically that's all. So first let's find the augmenting path. Basically it's very important that we have to find the shortest path possible in the residual graph. And it's going to be this path, so 5 plus 1 is equal to 6. As you can see, we are not able to find any other augmenting path that's going to be shorter. So it's going to be the shortest path possible in the augmenting path. That basically we have to get the minimum out of 5 and 1. So basically we have to consider the edge weights, and then we have to get the minimum out of these edge weights, because we are not able to flow 5 units when the capacity of a given edge is 1. So basically that's all, we have to take the minimum. And we can add the flow 1 in the G original flow network. So basically, as you can see here, we incremented the flow from 0 to 1, and here we incremented the flow from 0 to 1. And basically that's why we have to reconstruct the residual network, because as you can see now, the flow is 1 and the capacity is 1. So instead of a forward edge in the residual network, we are going to have just a simple backward edge. Okay, so let's see. As you can see, we have to update the residual network. We are going to have a 4 pointing from S to B. Why? Because we have flow 1. So there can be 4 units flown in this edge to get the 5 capacity. So that's why there's a 4. And there's going to be a 1 in the backward edge, because we are able to send back 1 unit. Okay, basically it's going to remain the same, it's going to remain the same, this is going to remain the same, but it's very important that we have a 1 flow and a 1 capacity. So that's why we are just going to have a backward edge with 1. Okay, we have to find the shortest path in the residual network. It's going to be the 4 plus 1. No matter what, let's consider that we go, for example, like this, 4 plus 7. It's going to be longer. So we are looking for the shortest path, and basically that's why we use breadth-first search. So we get the minimum out of these values, which is the min 4, 7. Why? Because if we would take the 7, then we would have to flow 7 units on an edge that has the capacity 4. Of course, it's not possible, so we have to take the 4. And basically, as you can see, we have to update the flow, because now we flow 4 units from S to A and from A to T. That's why we have calculated this 4 unit. Okay, and of course we have to recalculate and reconstruct the residual network, because as you can see, it has the 4 flow and 4 capacity, so we are going to have just a single backward edge in the reconstructed residual network. Okay, so as you can see, we have a single backward edge, a backward edge here as well, but anyways it's going to remain the same, and here we are going to have 3 in the forward edge. Why? Because we can push another 3 units in order to get the capacity. And we are able to send back 4 units because we have already sent 4 units from A to T. Then of course we are able to send it back from T to A. What about the shortest path in this given graph? Basically we have to find the shortest augmenting path. It's going to be this 4 plus 4 plus 3. we have to calculate the minimum out of these 4, 4 and 3. It's going to be the 3, so we can add this flow 3 in the G original flow network. So it's going to be added 3 units, it's going to be added 3 flow units, and it's going to be added 3 flow units. And that's why we are going to end up with this network. As you can see, there's going to be more and more backward edges because it's going to be 7 flow and 7 capacity. So there's going to be again a backward edge with value 7. Okay, so let's reconstruct the residual network. As you can see, we have a backward edge and the backward edge. So basically, we are not able to get from S to T anymore, which means that there is no more augmenting path, which means that this is the end of the algorithm. We are able to get the maximum flow, we just have to get it from the original flow network. So what's the maximum flow? Of course, the maximum flow is the maximum flow going out from source or the maximum flow coming into T. So basically we have a single edge with flow 4 and another edge with flow parameter 4. So basically the maximum flow is going to be 4 plus 4, which is equal to 8. We can end up with this result if we consider the sink. We have to add the edge weights basically with the flow parameters. So 7 plus 1 is 8 as well. So the maximum flow is 8. And we may pose the question that, okay, we have been talking about the minimum cut maximum flow theorem, which stated that basically the minimum cut is equal to the maximum flow. So what's the minimum cut in this situation? We start from the source and go until all edges are full. So we start at the S. We consider, for example, this edge. It's full. We have 4 flow and 4 capacity. What about this one? It's not full. We are able to go there. So let's visit vertex B. Okay, vertex B has 2 edges. The first one is, for example, this. We are not able to go there because it is full. We have 1 capacity and 1 flow. But basically, we are able to go here because it is not full, and we can visit A. But in this situation, we are not able to visit the T because it's full, this edge, 7 flow, 7 capacity. What does it mean? That we have basically the minimum cut. The minimum cut is when we partition the vertices into 2 disjoint sets. As you can see, we have a set with the sink T and we have a set with the source S. And basically, what's going to be the minimum cut? It's going to be all the edge weights that's going to start in one of the sets and going to point to the other set. So basically, we have this edge and this edge. This flow is 7, this flow is 1. So 7 plus 1 is equal to 8, which means that the minimum cut is equal to the maximum flow as we have discussed. Thanks for watching.